Hi, this is day 2 of integration by parts, where we learn something called tabular integration by parts. It's a technique for dealing with questions similar to the last example from the previous lesson, where you had to do integration by parts repeatedly. Before we get into that, I'd like you to try problems 1, 2, and 3 on your own first. If you're listening to this in class, then I would like you to try it with your aisle partner. And if you're listening to this at home, you're on your own. But please pause the video and come back with your answers for 1, 2, and 3 done. Okay, hopefully you're not cheating. But here are some questions similar to things we saw yesterday, if not identical. So question number 1, you can see off to the side my UDV box, and I just applied the rule. Fairly straightforward, I hope, and I hope this allowed any of you who missed the previous lesson to sort of catch up with your partner or by looking back at notes. Question number 2 we did exactly yesterday. This is a famous integral that maybe you've been curious about for a long time now, but now we know how to handle it because it requires integration by parts. So the integral of natural log of x is, as you read there, x ln of x minus x plus a c. The third problem was a doozy because it required integration by parts twice. So the writing in blue are my substitutions. So you see the line in green and the line in red are both using that first substitution box. But then the integral that I underlined in blue requires integration by parts a second time. And so you can see the substitution off to the side that works there. And my final answer is the last line in green. Okay, if there's anything there that you need to go back to, please do so. Or if you're watching this in class, ask the teacher to go back to it. Okay? All right, we are now going to learn a little bit of a shortcut, kind of an organizer for questions like number 3 that require integration by parts multiple times. And it's called tabular integration by parts because that word tabular is referring to a table. So that's how we will approach this. You can use tabular integration by parts even on questions that don't require more than one layer of integration by parts. And so I'm going to do example 1 from your notes a second time. And you can just see that it works out, even though you only need one layer of integration by parts. So the way that you set up your table, or the way that I set up my table anyway, is to write U and dV. And I've also seen it in some places where they labeled this with a capital D for taking derivatives, and this with a capital I for taking integrals. So I just mentioned that. I don't know which way is easier for you to think about. Off to the side, you also need a third column, which is an alternating sign column. That column is always going to start with a positive, with a plus. Okay? So then you set up your chart like this, and similar to the way that we determine what is U and what is dV normally, we just think about those same ideas. So in this problem that we have, the thing that we would let be our U is the x. So we will do that, which means the rest of it is our dV. Now, when I do this tabular integration by parts, I don't bother writing the dx. This is a shortcut-ish kind of thing, and it works out okay to not do that, okay, to not include the dx. So we'll just cut ourselves some slack on that. In this last column, as I mentioned, this always starts out positive, and then you just alternate signs. Not sure exactly how many we need. I think maybe 4, but we'll just write some signs, and if you don't use them, that's okay. Then, once you have it set up, then you take derivatives and integrals. Okay, so in the left column, if I take the derivative of x, I get 1. If I take the derivative of 1, I get 0. Please write so you're writing in straight lines. This actually works better with notebook paper than just blank paper. And then in the middle column, we're going to anti-differentiate. And the antiderivative of e to the x is just e to the x. Okay, now I did stop here. And the reason that I stopped was that zeroed out. It went away. Okay, and so once you get to a 0, then you quit. Okay, and then the way that you use this table to find your answer is to read along diagonals. So you start in the upper left-hand corner, and you just go across like this along a diagonal, and you multiply those elements. So that would be x, e to the x, and a positive 1, if you want to call it that. So that just stays as it is. And then the next diagonal I would have is this guy, which is going to be minus e to the x. And then when I get to the 0, you can see like anything that I multiplied with the 0 is going to be 0. That's how you know you're done. And since this is actually the result of an integration problem, we have to remember the plus Charlie, and that's that. Okay, so this hopefully matches exactly what we got for question 1 before. Is it? Oh, good, we did it right. Okay, so that's tabular integration by parts. That's just an organizing sort of way to get through an integration by parts problem, okay? Now, the next question I have here is the one that did require integration by parts twice. And I think here you'll see the time savings, okay? So we'll set up our table, U, dv, changing signs. Okay, we can remind ourselves that here we're going to take derivatives, here we're going to integrate. Okay, and then we'll just set up our chart. And writing nice and straight across, very important. Okay, so if this were a normal, just integration by parts problem, I'd let x squared be the u. Sine of x dx would be my dv, but I'm going to leave off, or sine of x dx would be the dv. Oh, trying to talk too fast. And I don't need to worry about the dx in the chart. We just let that lie. Over here are alternating signs. Don't know how many I'll need, but I'll go with how much I can fit. Okay? Now, take derivatives. So x squared becomes 2x, 2x becomes 2, 2 becomes 0. And that's going to be all we can do. Okay, so we're going to have to write at least, we're going to have to write 4 rows in the next column, okay, to match up with where that zeroed out. Okay, so the integral of sine would be negative cosine. Here it's tricky to watch your pluses and minuses. The integral of negative cosine would be negative sine, and the integral of negative sine would be positive cosine. Okay, and if you're not sure, sometimes I get nervous about the pluses and minuses with this. You can always just read up the column and make sure your derivatives make sense, right? Because that's the test. All right, now we do diagonals. So we go right through here, and we multiply those together, and we would get negative x squared cosine of x. And then our next diagonal would give us positive 2x sine of x. And our next diagonal would give us positive 2 cosine of x. And then if we did another diagonal, it would zero out. So this is time to write Charlie. Okay? Compare that to problem 3. Okay, we got the same answer, but I do think this is easier. It doesn't maybe show the math quite as much, but sometimes a gimmick is a nice thing. Okay? Question 6 is a different sort of integral. This is one where if I set up my chart, nothing is going to zero out. If I have e to the x as my u, I'm just going to keep getting e to the x's. If I have sine for my u, I'm going to go sine, cosine with some pluses and minuses flying around, okay? So this is a different sort of problem, but it is manageable with this technique. So let's set up our chart, and I'll show you how this variation can play out, okay? So I'm going to choose, it doesn't actually matter in this case which one is which, because neither of them is going to zero out or get better if I take derivatives, but I'm going to choose to put sine here, okay? And then I'm going to have my e to the x be this part, and as we mentioned, we always start positive and then alternate, okay? And what I'm going to do is first fill in the middle column, I guess, because that's really easy. I'm not really sure how many I need. But what I'm going to do as I continue on to that first column is I'm going to pay attention for when I see a row or a line across in my chart that has the same elements as what I'm beginning with. Okay, so I don't know if that makes sense to you yet, but just kind of stick with me for a minute, and I think it will. So let's fill in our first column. Sine has a derivative that is cosine. Cosine has the derivative negative sine. I think I already found the thing that I was watching for, which is this row. Okay, that row of writing has the same elements as my original integral does. Okay, so that is going to be where I can stop in this case, believe it or not. And then this is what happens. Okay, see if you can understand the rationale behind it. Our original problem is, let me look back again, e to the x sine of x. This will work better. This kind of problem works better if you write down the original problem and then write down the result of the tabular integration by parts. Okay? So in my table, I see that I've got this. Okay? That diagonal is e to the x sine of x with a positive, so no sign change. And then my next diagonal is this guy, which is going to be minus e to the x cosine of x. Okay? Now, as soon as you have the diagonal, that I say pierces. I don't know why that has to be so violent in my head, but it does. Once you have the diagonal that pierces that magical line that has the same elements as your original, then you stop doing diagonals and you're going to read straight across horizontally. And that horizontal reading is actually still an integral. So we'll write minus the integral, and I'm reading this, minus the integral of e to the x sine of x. I'll put a dx to keep it legit. Okay, now look at just that line of writing. Do you see how you have the same element here and here? Why don't you put those on the same side, like collecting like terms? Then we would have two integrals of e to the x sine of x being equal to these other pieces from before. Okay? And since what we were trying to solve for in the first place was this integral, to solve for it, all I need to do is divide this 2 over here. And because I did integrate, I should have a constant of integration. And that's it. This part here is the answer to the original integral. Okay? So that is what I might refer to as like extended tabular integration. Some people call it party trick integrals. I can see that. You probably want to show this off at your next party. Talk to you guys later. Good luck with the problems.